Hello, everybody. My name is Andriy Smolyanyuk, and in this session, I will talk about quasi-harmonic approximation and how can you use AFLOW QHA model to calculate thermodynamic properties. But before I begin, I want to list you a few books if you will have an idea to continue and deepen your knowledge. And these first two are good introductory books. And if you feel that you want to have some adventures, you can go to advanced section. So in previous section, you were quite familiar with harmonic approximation, but you might have wondered what it will be if you start including third term, fourth term, and so on, which we will call anharmonic contributions. And now I will give a brief idea of what actually have we missed by truncating this term at second contribution. So at first, in harmonic approximations, phonons are independent, so they don't interact, and even if they meet each other, they really don't care. But when you start introducing anharmonic terms, interaction starts and phonons start scattering on each other. And you can see here on animation an example of how two phonons collide and produce another phonon. And the first row actually describes possible scattering with third order, and where you have three phonons interacting. And the second row is about fourth order, where you have four phonons involved. And if you would attempt to calculate, for example, thermal conductivity in harmonic approximation, you will find the answer to be infinity, which is, of course, non-realistic. And you really need to introduce contributions beyond the harmonic ones to get a finite thermal conductivity. And here is an example where AAPL module was used to actually do a calculation. Another important effect is that phonon frequencies in reality, they depend on temperature. And this dependency is not communicated in harmonic approximation. And here you see an example of so-called soft mode, and the dependency is so basically square of frequency linearly depend on temperature. And as you can see, at zero temperature, which will correspond to harmonic approximation, if you do a calculation, you will actually get an imaginary mode, which will mean that your structure is unstable. But when you rise the temperature, you actually have a positive Ohmrod square, which means that you have a stabilization by anharmonic contributions. And this can lead you to a study of phase transition. A good example will be lead TO3, which is a ferroelectric material. So at low temperature, it's tetrahedral, but at high temperature, it's cubic. So if you try to do a harmonic calculation on cubic structure, you will see imaginary modes. But actually, after some, if you can include an harmonic contribution, after some temperature, you will stabilize the structure. And here is an example for, again, one particular mode. And you can see the dependency of frequency on temperature. But besides that, also frequency depends on temperature in not in a direct way, but it depends on volume. And as we know, solids expand when you try to hit them. And to capture this effect, to capture effect of thermal expansion, you need to have anharmonic potential. So here is an illustration of an idea why when you have a harmonic model, you cannot have this effect at all. So in harmonic model, their potential is a parabola. And these horizontal lines, they correspond to different temperatures. So the higher you get, the higher the temperature is. And as you can see, the atom moves on the right and on the left with the same amplitude. And on average, no matter how high temperature is, you have, say, on average, they stay in the same position. And it is reflected with this dotted line. However, when you have an anharmonic potential, when you start into increasing temperature, again, each step here is some increase of temperature, you see that atom moves more to the right than to the left. And in overall, you get an expansion of your crystal. Now I just want to show you a few examples of thermal expansion in real life, because thermal expansion will be a key to the approximation we will be using today. So since we know that substances expand on temperature, we can actually use this effect to measure the temperature. And that was the idea of a regular thermometer. Also, if you're a civil engineer and you need to build some construction, you need to take it into account. And in this image, you have an example of a gap introduced in a bridge, because its length is different when the temperature outside is hot, or when the temperature is it's cold outside or it's hot outside. And also, if you do a railroad, you also need to do it carefully, because you can have an effect of railroad buckling on high temperature. And one example, which probably all of you have encountered, if you had, for example, chemistry classes where you had to heat some liquid in a glass tube with open fire, if you don't do it carefully enough, your tube might break. And actually, it's coming that if you subject glass to a rapid temperature change due to thermal expansion, thermal stress will be introduced, and it might lead you to a fracture. So now we know that anharmonicity is important and we want to use it, but we cannot do it in an exact way because it will be very computationally demanding. But as I mentioned, Phonon frequencies do depend on volume, and it's very easy to do a DFT calculation for various volumes. So we can exploit this idea, and this is the essence of a quasi-harmonic approximation. So here I show you a plot with aluminum, and a solid line corresponds to a volume at equilibrium, and I artificially change the volume to add some and to compress it. And as you can see, with, for example, this dotted line, when you increase the volume, your frequency actually goes down. And when you compress the structure, you start getting a higher frequencies. And by having this information, you might wonder, okay, but I see that in different for different KQ points, you have actually different effect, and you want to quantify it somehow. And to do this, you can take a derivative, which actually tells you how much things change with applied change. And this is the idea behind the Grüneisen parameter. Here's a definition. And if you do this computation, you will get a plot on the right. And now you can actually quantify how much of degree of anharmonic contribution comes to each phonon. And in harmonic model, this gamma will be 0. But here, the higher gamma is, the higher the value, the more contribution are coming from anharmonicity. And okay, now we have a lot of numbers here, and you might want to make a weighted average by using as weights using heat capacity contribution from each mode. And it gives you important quantity which we can use to estimate thermal conductivity and also estimate thermal expansion. Okay, so yeah, now I wanted to give you an example how can actually you do computation with QHA. So as you already know, we can use AFLOW proto and specific prototype to generate a structure, and then you can use a module to specify QHA, and it will uncomment the QHA block for you. But please have in mind that QHA depends on APL, because we are actually doing harmonic calculations for different volumes. So we want to change APL settings too. For example, if you're making a calculation with a metal, you don't want to have a polar correction. Or, for example, you might decrease the number of atoms in your system if it's too big for you. As for QHA, there are two different flavors of it. We have just finite difference calculation of Grüneisen parameters. It covers the block I just showed you already. and we have an calculation which involves a creation of state. I will talk about it in a few minutes after we do a break for exercises, and you can turn it on with EOS off. And you do a usual flow -- run to run AFLOW. Now it's time for exercises, and probably we will do breakout rooms. So we will have 2 exercises. First one will be to actually generate a flowing file with the command I showed you before. Then you will need to go to the directory which AFLOW will create for you. Just make sure that AFLOW QHA calc is uncommented. If it is commented, you need to uncomment by yourself. And if it will be commented, AFLOW will proceed with path run, which you don't want to do. Make sure you do the following changes. For this, we want to switch relaxation off, we want to switch EOS off, and we want to have GP finite diff on because we want to just calculate Grüneisen parameters. And you can specify the change in volume you wish to have, and you do it with the keyword GP distortion, and it will number in percentage of volume changes. It will automatically do a compression and do an expansion of the volume. And then you use AFLOW run to actually run a command. And in second exercise, I have a pre-calculated data for you because it takes some time. Again, you will need to go to AFLOW in file and command AFLOW QHA calc line, do a changes to switch off EOS mode, switch on GP finite difference calculation, and select the value of this distortion to be 3. Then you do a run. And in case of successful run, you will have 3 files created. So the first file will give you the data of average Grüneisen parameter, basically the one which were used to produce this plot. The second one, GP diff out, is actually your Grüneisen parameter dispersions as on this plot. And it's saved in an eigenvalue format of us. And third one is a bit different. It's you just have a mesh of k points, and for them you calculate Grüneisen parameters. So once you have them, you can ask AFLOW to plot dispersion for you. And I encourage you to do this. You have 2 commands. One is a bit longer, another is a bit shorter. And then you can open GP average out file and examine by yourself a Grüneisen parameter at 300K and 930K. I hope you were able to do the exercise, but I will now show you real quick what you should have done with it. And I'm deeply sorry, there was a mistype on my second exercise slide. There should be S in dispersion. Sorry for that. We will update slides later. So for the exercise one, the idea was to run an AFLOW command based on prototypes of FCC structure for aluminum. And when you have a QHA module selected, it will uncomment the QHA block for you. So as you can see, QHA block is uncommented. And in APL, we want to switch relaxation off. We want to select distortion 3 and switch to a finite difference mode. And we want to switch off an EOS. And with that, you can run AFLOW. It will take a few seconds. And as you can see, 3 directories were created. First one corresponds to 3% compression volume. Second one is original volume, and third one is 3% expansion volume. And if you go into any one of them, you will have an AFLOW file for APL calculation uncommented for you. And it takes all of the APL settings from the main parent file. And for the second exercise, I actually provided you the data for calculated data for first one. So idea here, you need again to apply some changes. You want to switch off relaxation. You want to uncomment QHA. You want to have EOS to be equal to off. GP finite diff actually switch to on, and distortion set to 3 because you pre-calculated it with a change of volume in 3. Then you can do a run. And you can see that 3 important files which I mentioned for you are created. You can use AFLOW, prot, plot, Grüneisen, dispersion commands to plot them. Or you can use a shorter one, which I prefer usually. It will create a PDF file with a plot. And you can go ahead and plot it. Although there is some problem, so I recommend you to rename file something else. And you see the plot the same as I showed you in the presentation. And the last part of exercise.
Hey, Andriy,
Yes.
quick question. Can you pull up the plot again?
Yes.
We had a very astute participant who asked why is it that we see this discontinuity at gamma and we don't see one between kappa or K and U where there is a discontinuity in the band structure?
Yes, sure. It's a good question. And the deal is, so discontinuity happens for acoustic modes, and for aluminum we have only acoustic modes. And if you remember your phonon dispersion at gamma, you actually have a 0 frequency. So basically gamma is a special point because you have a frequency to be 0, right? And if you think of taking a derivative of gamma, it will actually omega, which is 0, which will give you 0. But when you move a bit off the gamma point, you actually have a finite value of Grüneisen parameter. Also, if you look on a different path, you might have that, let's say, gamma x and, for example, k. You have one slope for gamma k, but I'll try to exaggerate it. A different, no, it's not very good. Let's do it like yellow. A different slope, right? And you have a different slope. And in this example, let's imagine that these two are two degenerate modes in gamma k direction, but they are not degenerate in gamma x. But still, when you take a derivative of one and another, you will get two different. You will get gamma 1 value here. You will get some different gamma 2 value here. And on the other side, you will probably get some gamma 3, which will be different from them. And that's why you have these discontinuities. So if I go back to the plot, as you can see, for gamma L, you have a degeneracy, which you don't have for gamma K. And that's actually correspond to having 2 Grüneisen bands on the right and 3 Grüneisen band on the left.
Ah, interesting.
Yes. So it's a
Okay.
bit similar to the case that Dr. Asters had with non-analytic contributions. So now gamma near gamma, Grüneisen parameter near a gamma point actually depends on the path which you approach it. And itself at gamma, you cannot really define it.
Okay. Perfect. Thank you very much.
Yeah, no problem. That was a really good question. And just to wrap up this exercises, I wanted you to check values for 300K and 920K. So you might want to uncompress the file, QHA, GP average, and you can open it with, for example, gedit. And you can see that at 300K, you have approximately 2.27, and then 920, it's 2.26. So very little change. And that's what I wanted you to see. So the second part of my talk will be about how to get another thermodynamic properties, like you might be interested in the bulk modulus or actually thermal expansion. And for that, what you need to do, you need to calculate the free energy. So once you have a free energy of your system as a function of volume and temperature, you basically know everything you need to define all of the thermodynamic properties of interest. And in our case, you have three terms which contribute to free energy. It's a static DFT calculation, E0. It depends on volume. And you have free energy coming from electrons, which is defined by internal energy and electronic entropy. And this information you get from electronic dose, which here is defined as GE. And capital F is a Fermi-Dirac function. And vibrational free energy you can get in the way as Marco described to you, where you use phonon dose for that. And once you have this, I mean, we have a little problem because we are doing calculation for some finite volume, and we can only have a discrete set of calculations, especially if you're doing a phonon calculation. They might be very expensive, and you want to limit the amount of calculations you're doing. So the way to go around of this is to use some analytical expression to fit your free energy volume data points. And in our case, we use so-called equation of state. It's an equation which relates state variables. In our case, it's volume and free energy itself. And in QHA, you actually have three different analytic forms to use. First one is monogam EOS. For this, you need to do at least, this is a minimum of 4 calculations for different volumes. And you can select a model with a keyword EOS model. Here's an analytic formula, how it looks like. And you may note that this one is non-analytic, non-linear. So you need to use a bit different method if you want to use it. Second one is Birch monogam. And we provide 3 different variations of different order, starting from a second one. For second one, you need to have at least 3 volumes. For third one, 4, and for fourth, you need to have 5. And it's a simple polynomial with even power of even number divided by 3. And the third one is stabilized Cellium model, which was actually derived for a Cellium, which is a homogeneous electron gas. You again need to have 4 volumes, and you specified it with SG keyword. And it looks similar as a Birch monogam, but now you have not only even, but also odd powers. And what you can do, you don't need to run AFLOW for each of them. You can actually use a comma to specify as many different models as you like. And it should be pretty useful. So having this analytical model, we can actually do a minimization. And when you find a minimum in free energy, you can estimate the equilibrium volume for a corresponding temperature. So APL provides you free energies for different temperatures. So we can now do repeating this procedure again and again for each temperature. You can have a dependency of volume on temperature. And here is an example for carbon in a diamond structure. And as you can see, it indeed volume increases with temperature. And you might think that you have quite a little information, but actually right now you have a really powerful tool and you can study phase transitions. So we can calculate free energy at each equilibrium volume at each temperature for different structures. And here I have an example of tin with alpha tin is a diamond structure and beta tin is the trigonal structure. So what you do, you plot free energy temperature dependency for each of them. And for each temperature, if you follow the structure with the lowest free energy will actually be the stable one. So at low temperature, alpha tin is a stable one. And when you reach some critical temperature, you actually have a transition to a beta tin, which is the trigonal one. And as you can see here, for example. And since we have a volume with temperature, for your application, you might actually want to know what the coefficient of thermal expansion is. And it is defined as a logarithmic derivative of volume with respect to temperature, like here. And you can ask, AFLOW is doing this computation automatically, and you can ask it and make a plot. Here is an example for diamond structure with carbon. And the next property you can do is a bulk modulus, which is a second derivative with respect to volume of free energy. And I just want to give you like a simple rule of thumb that, for example, material with a bulk modulus of 100 GPa will require 1 GPa pressure to be applied to shrink by 1% of its volume. And here you have some table of some materials with bulk modulus. And the higher bulk modulus is, the more your material, the more stiffness your material has. And as you know, diamond is a very stiff one. And for example, if you look on a chalk or a regular salt, you see the bulk modulus is really small. And again, here is an example of a plot of bulk modulus with temperature for our diamond structure of carbon. And the last property you can extract is a heat capacity. So heat capacity in general tells you how much heat you need to apply to a system to increase its temperature by 1 degree. And you have two possibilities. So usually at experiment, we operate with constant pressure. So we have an isobaric heat capacity. But in calculations, for example, as it was with APL module, we actually have a constant volume. And as you have seen with APL, you can only get the one with constant volume. But now having information from QHA, when you have a dependency of volume on temperature, bulk modulus, thermal expansion coefficient, you actually can do a correction and you can extract a constant pressure heat capacity and maybe compare it to an experiment. And you can see it with a dashed line, you can see heat capacity at constant pressure. And now I want to recap of what properties we have. And at the beginning, I was talking about average Grüneisen parameter. And when you have all of these properties on top of the slide, you can actually have another way to calculate Grüneisen parameter from using thermal expansion, bulk modulus, and so on. And actually, you can see that there is a proportionality between the Grüneisen parameter and the thermal expansion. So a bit of a special topic for today will be to discuss a quite peculiar effect of negative thermal expansion. So I told you that solids usually expand on heating, but there might be an effect for some of them when they actually compress. And you can see here is a silicon with diamond structure, and at low temperature, we can see that the thermal expansion coefficient is actually negative. And that might be useful for some application. For example, if you create a metamaterial, which is a sandwich of two materials, you can select one to have a positive thermal expansion and another one to have a negative thermal expansion. And in overall, this material will have a zero thermal expansion, which might be useful for some applications. And to get a bit of an idea of why it is happening, so for crystals where you have rigid units like, for example, octahedron or tetrahedron, as was the case of silicon, if you move this atom left, right, it will actually correspond to compression and expansion of octahedra. But actually, in reality, what happens, at some cases, it's easier for atom to move actually up and down than to move left and right. And atom, for example, if this one moves up, then this will try to move right. This one will go down, this one will go left, because octahedron wants to conserve its shape. And it will correspond to rotation of octahedra, as you can see on the right figure. And when you rotate them, you actually kind of compress your structure. As you can see, the volume of a cell gets smaller and smaller. And with the tools we have available, we can actually go into details of why it's happening and what is responsible for that. And one useful quantity for that is Grüneisen parameter. And as I said, that at zero, you will have a harmonic. For harmonic model, you will have Grüneisen parameter to be zero. But you might wonder what happens, and can Grüneisen parameter be negative? And yes, it can. And actually, a negative Grüneisen parameter shows you which modes are responsible for negative thermal expansion. And here you have an example of a particular mode at X and at L Q point. And as Dr. Esther explained to you, you can visualize this mode with AFLOW program. And as you can see, these four atoms, they try to move down, and you see the same on the picture on the right. And this atom moves up, and you see the same on the right here. And again, you can make an animation, and you can do a visual inspection of this particular mode. So now it's time for a third and fourth exercise. So in third exercise, we want to actually generate a flowing file for a calculation of thermodynamic properties I just described now. And you want to make sure that AFLOW QHA calc is uncommented. You want to switch polar to off and relax to off in APL block. And EOS, by default, it will be on, so we don't need to do anything. We have this parameter which controls how much your structure will be changed. And it tells that start with 3% compression, go to a 6% expansion with a step of 1%. And you will run and you will see how many structures it will generate. And fourth exercise will actually correspond to the third one, but I provide you a calculated data. And in case of successful run, we will have AFLOW QHA thermal file created, where you will have all of the properties as a function of temperature. And you can use plot thermo QHA command to plot them. And I encourage you to open the PDF files and have a look. And you will have a short exercise for the last, just to look on the numerical values of thermal expansion and heat capacity, just an example. There was a question in chat about what are advantages with different EOS models and limits, and when should you apply which model. So in general, I would say the quality of models increases when you go down this list. The first one was monogam EOS. And experimentally, they usually had the problem with it that it was not very good in explaining data for a high pressure. So birch monogam should be better, and even better should be stabilized helium EOS model. So main difference would be how they behave on compression. But also in our case, usually if the system is well behaving for properties we extract from this, it will not make too much of a difference. For example, thermal expansion can be varying by 1–2%, which is not a very big deal. But another thing to have in mind is that if your data is not so good, you might get into troubles to have a fit. And you should keep in mind that monogam EOS is non-linear model, so it requires a bit different type of numeric algorithms to actually perform a fit. And birch monogam and stabilized helium EOS is a linear one, so that should be easier and a bit more robust. Also with second order birch monogam 1, the assumption is that variable like here B prime, which is actually pressure derivative of bulk modulus, in BM2 model, it is assumed to be 4. So keep that in mind. And you can use it as a sanity check if your fit for other models were good enough or not. If you have too big of a difference, for example, for a thermal expansion, it might be that you have some problem of your data and with your data, and you need to examine it more fully. Generally, I would recommend to stay with stabilized helium EOS model. It's usually robust enough. If there are no more questions, I will actually show you how would you do an exercise. So for a third one, you need to run again AFLOW QHA command. Now we have a diamond structure, so it will be different designation. Space group 227, silicon, module equals QHA to do a QHA run. We can edit AFLOW in file. Oh, we first need to go to the directory. Edit AFLOW in file. And as you can see, QHA is uncommented. We want to switch relaxation off for this one, and it's switch polar corrections off too. And we want to change distortions of volume, which we want to apply. And then we are safe to run AFLOW. And from -3 to 6%, it's 10 volumes in total. Okay, it will take some time to generate files. But here you will have 10 directories with phonon calculations and 10 directories with static calculations, which you can run using AFLOW multi-command. And I will explain a bit better the structure using exercise 4, where I have a pre-calculated data. So if you go to a phonon directory, for example, corresponding to 3% compression, you will see that you have phonon displacements directories created for you for a supercell. Here you have a harmonic force constant file, and you have AFLOW in with APL uncommented for you. And in a static directory, we are just doing a regular static run because we need to have a static DFT calculation for a specific energy, static energy from DFT calculation for a specific volume, which we cannot extract from a Fanon calculation. And here it will, QHA will take it from an outcar file. Then the idea was to do a really small modification of AFLOW file. You should make sure that QHA is uncommented, and you had to change a range from -12 to 3, -16 to 6, and from 3 to 1. And with that, you're safe to run. It will take some time. Okay, I actually done this exercise before, so I can just show you results. We didn't really need to wait. And as you can see, in case of successful run, you should have AFLOW QHA thermo file, and you use AFLOW plot thermo QHA command to plot. And so we can see you have a few files: isobaric heat capacity, isophoric heat capacity, free energy as a function of temperature, Grüneisen parameter as a function of temperature, bulk modulus, thermal expansion coefficient, and equilibrium volume as a function of temperature. And for example, we can open a thermal expansion and see by ourselves that it's actually negative for low temperatures and it decreases with temperature. And last one, what I wanted you to do is open AFLOW QHA thermo file. If you're using Vim, you can use that no-rep to have it in a bit better form. And thermal expansion should be a fifth column. So for 70K, you will see it's a negative, minus 0.14 for this calculation. And for 300K, it's about 0.97 to the 10 to the -5 power divided by K. And for a heat capacity at 1200K, it will be 6 column and around 2.96, which is close to a limit of 3 Boltzmann constants per atom. And that should be it with the exercise.